Linear equations are best understood as relationships, not just formulas. A straight line tells you how one variable changes with another in a perfectly consistent way. And that consistency is the whole point of this chapter. Once you understand slope and intercept behavior, the rest becomes much easier to read visually. In CAT-style questions, this is less about algebra alone and more about mapping relationships quickly. A linear equation is basically a mathematical straight line, and that is what makes it so clean compared with higher degree equations. The slope acts like the rule that governs change, while the input-output structure keeps everything balanced and predictable. The important thing to notice is that there are no curves and no exponent traps here, which means the logic stays simple if you read the equation carefully. That is why these questions often reward clarity more than calculation. The real value of linear equations is that they convert word problems into equations. That is the whole skill. Take a verbal condition, turn it into a ratio, balance, or intersection statement, and then solve. The slide makes a strong point about unique variables and the number of equations needed, which is a useful exam rule. If there are two unknowns, you need two independent equations. If there are three, you need three. That simple logic prevents a lot of guesswork. The standard form, ax plus by plus c equals 0, is the backbone of linear equations in two variables. Here, a and b are the structural weights, x and y are the unknowns, and c is the fixed constant. The important observation is that a and b cannot both be 0 because then the equation would stop being linear in any meaningful sense. This is one of those small technical details that often becomes a direct theory question, so it is worth keeping precise. This challenge problem is a classic mixture question. You are told the total number of books in 2010 and 2015 along with the growth rates of fiction and non-fiction, and the task is to find the fiction count in 2015. What matters here is not just arithmetic, but setting up the right system with the right variables. CAT often hides linear equations inside everyday contexts, and the trick is to translate the story into a clean algebraic structure before solving. The standard solution builds two equations, scales one to eliminate a variable, and then solves step by step. It is mechanically correct and easy to follow, but the warning on the slide is important. This style costs time and increases the chance of calculation mistakes. In a timed exam, a reliable method is not always the best method if it is too slow. The bigger lesson is that linear systems should be approached with a strategy, not with blind expansion. The topper's approach shows why pattern thinking wins. Instead of solving everything from scratch, you assume the minimum growth first, calculate the base, find the gap from the actual total, and then assign that gap to the extra non-fiction growth. That gives the fiction count immediately. This is exactly the kind of mental restructuring that separates average solving from high-speed solving. When the relationship is clean, the shortcut is often faster than the full method by a huge margin. This slide shifts from arithmetic into line behavior. Systems are really about ratios, not just addition. So the first thing to check is whether the lines intersect, run parallel, or coincide. Intersecting lines give one unique solution, parallel lines give no solution, and coincident lines give infinitely many solutions. The common mistake is trying to solve equations blindly even when the line pattern already tells you the answer. If you can read the geometry first, you save both time and effort. The speed hack here is especially useful in competitive exams. Instead of solving the system the long way, compare coefficient ratios first. If the ratios are unequal in the right way, you know the solution type immediately. If they match in a certain pattern, you know whether the lines are parallel or coincident. This is a classic elimination before calculation strategy. The key takeaway is simple. Compare coefficients first, calculate later. The advanced formula introduces Cramer's rule, which is the determinant method for solving linear equations. The core matrix and determinant structure allow you to compute x and y directly from coefficients and constants. What makes this valuable is not only its elegance, but also the clear warning. If the determinant becomes 0, the lines are either parallel or coincident. So you should stop and think before calculating further. That is a very important exam insight because it prevents wasted work. This final cheat sheet brings a chapter together in a compact revision frame. The standard form is ax plus by plus c equals 0. The key rule is that the number of equations must match the number of variables, and the high-speed shortcuts are shift and gap logic and coefficient ratio checks. The final strategic reminder is the best one. Do not treat equations as isolated expressions. Read the relationships they represent. That is the mindset that makes linear equations feel easy instead of mechanical. Quadratic equations are best understood visually, not just algebraically. Think of every quadratic as a parabola, a curve that tells a complete story. It has intercepts where it touches the x-axis and a vertex which represents either a minimum or a maximum point. The key idea here is that solving quadratics is not about memorizing formulas. It is about understanding the shape and behavior of this curve. Once that clicks, everything becomes faster and more intuitive. A quadratic equation is essentially a degree 2 polynomial that maps into a parabola. The coefficients a, b, and c are not random. They directly control the shape, position, and width of the curve. The discriminant acts like a reality check, telling you whether the graph actually touches the x-axis or not. And the roots are simply the points where the curve intersects the axis. If you follow this logical flow, coefficients to discriminant to roots, you'll never feel lost in a question. There is a deeper reason why quadratics are so powerful. They are predictable because the discriminant immediately tells you the nature of roots. They are symmetrical, meaning both roots lie equally spaced around the vertex. And they are incredibly useful for optimization problems where you need maximum or minimum values. That symmetry is the hidden weapon. Most shortcuts in CAT rely on exploiting it rather than calculating blindly. The quadratic formula is often treated as the main tool, but it is actually just one part of the story. The expression inside the square root, the discriminant, decides everything. If it becomes 0, both roots merge into one point, and the curve just touches the axis. Another key insight is symmetry. The two roots are always equally spaced from the center line x equals minus b over 2a. That midpoint idea is extremely useful in faster solving. This problem is designed to test your conceptual clarity under pressure. A student misreads the coefficient and ends up with incorrect roots, but the product of the roots remains unchanged. That is the key observation. Even when the equation changes slightly, some relationships stay constant. The exam is not testing calculation here. It is testing whether you can track invariants like product and sum under small errors. The standard method solves this step by step. First, compute the product using wrong roots, then rebid the correct equation using the actual coefficient, and finally factorize to get the correct roots. It works perfectly, but it is time-consuming. In a competitive exam, spending 40 to 50 seconds on a single question is expensive. The lesson here is not that the method is wrong, but that it is inefficient. A topper approaches the same problem very differently. Instead of solving from scratch, they directly use the relationship between sum and product of roots. The product stays 30 and the sum becomes minus 13. So the answer is immediately minus 10 and minus 3. This is pattern recognition at work. The moment you shift from solve to recognize, your speed improves dramatically. The vertex plays a crucial role in optimization questions. The x-coordinate of the vertex is always minus b over 2a, and that gives you the exact point where the function reaches its minimum or maximum. If a is positive, the curve opens upward and gives a minimum. If a is negative, it opens downward and gives a maximum. One common mistake is forgetting to divide by a when applying sum and product rules. That small error can completely change the answer. There is a powerful shortcut when dealing with sums and products. Instead of plugging values into the quadratic formula, you can directly construct the equation using x squared minus sum x plus product equals 0. This approach avoids unnecessary calculation and works especially well when the question focuses on relationships rather than exact roots. The key takeaway is simple. If the question does not demand actual roots, do not waste time finding them. This advanced formula connects the difference of roots with the discriminant. The square root of the discriminant essentially controls how far apart the roots are, while the coefficient a controls the scaling of the graph. This becomes extremely useful in questions where you are asked to compare or constrain roots rather than find them explicitly. It is one of those formulas that looks complex but saves a lot of time when used correctly. Everything comes together in this final summary. The quadratic formula remains central, but understanding the discriminant is even more important. The sum and product relationships provide shortcuts, and the vertex gives insight into optimization. The biggest mindset shift is this: do not treat quadratics as algebra problems. Treat them as graphs you can visualize. Once you start seeing the curve in your mind, the answers come much faster and with far fewer mistakes.